Okay, this question we have a pulley on a slope. Now, it's always a good idea to get your diagram right with these kind of questions. So let's fill in all the information. Key points. A has a mass of m. So actually let's just make that a bit bigger because we're going to need to resolve that later on because it's on a slope. So that has a force of mg going down. The other end of the string is attached to a second particle B, which has a mass of lambda m. So let's mark that on. Lambda mg going down. Lambda is constant. Okay, particle A is in contact with a rough plane inclined at 30 degrees. Now, because it's rough, that means there's going to be friction acting, friction opposing the motion of A. And so I'll just highlight that. The pulley is smooth, so no forces acting on the pulley, no restrictive forces. And this last bit, we don't really need any of the last bit in terms of sketching our diagram. So let's mark on the tension. If we're talking about B, the tension is going up here. If we're talking about A, the tension is going in this direction. Now, other forces that are going to be acting on A, we will have the normal contact force, which is always perpendicular to the slope. Let's call that R. And we will probably, we're going to need to resolve this mg at some point. So let's just do it now, shall we? So I use a different color. If we draw a line going down here, that angle there will always be 30 degrees, and which makes this mg cos 30, and this over here will be mg sine 30. Okay, that's because the right angle will be there. Okay, now I think we're just about ready to actually look at the question now. If we look at the question, what's it actually asking us? It says A is on the point of moving down the plane. Oh, right. See, I thought that A was going to be going up the plane, which is why I drew the friction in this direction here. But since it's not, so it appears I was wrong, and it's actually going, well, it's trying to go down the slope in this direction. So A is on the point of moving down the slope, which means that this friction is not acting in this direction. So I'll just cross that out, and actually the friction must be going in this direction instead. Okay, and since it's on the point of moving, that means that the friction is at its maximum, which means we'll be able to use this formula F max equals mu R. Okay, so we'll probably have to use that in a minute. So resolving some forces then, if we look at the forces on B, so if we resolve vertically on particle B, we can see that T, the tension going up, must equal lambda mg, but it tells us in the question that lambda equals a quarter, so that's going to be a quarter mg. Okay, so T is a quarter mg, so we can say that that T there is a quarter mg. Now, if we resolve parallel to the slope, looking at the forces on A, again, nothing is moving, there's no acceleration here because it's on the point of moving, so that means all the forces up the slope on A must equal all the forces down the slope on A. Now the only forces going down is this component due to gravity, so all the forces going down the slope are mg sine 30, and all the forces going up the slope, well, we have this tension here. We have the tension, which we know is a quarter mg, and we also have the friction, which we know is at its maximum because it's on the point of moving. So we could probably simplify this now. Sine 30 degrees is a half, so if we rearrange this, we'll have a half mg minus a quarter mg equals the friction. Now, as I said before, this will be maximum friction, so this will equal mu r. Now r, maybe just use a different color here. Looking at the diagram, r is the only force perpendicular to the slope going up, and that will equal this force here. So r will equal mg cos 30. So we can write that down instead of this r. Let's just get rid of this for a minute, because our equation is now going to be oh, by the way, half mg minus a quarter mg is just going to be 1/4 mg, so that equals mu times r, but as we just discussed, r is mg cos 30, and that means that the mg will cancel on either side, and so mu, if we get mu on its own here, mu is just going to equal 1/4 divided by cos 30, and if I type that into my calculator, 0.25 divided by cos 30 equals √3/6. In B, it says show that the value of lambda must be less than 1/2. So if we find an equation involving lambda, we know from this, we know that T equals lambda mg, but that doesn't really help us. So if we look at the forces parallel to the slope again, you can see that the frictional force F, that equals this component of gravity mg sine 30 minus the tension in the rope. Okay, and we know that is lambda mg from here. Now the frictional force is a rough slope, so we know that the frictional force must be greater than 0. So that means that all of this must be greater than 0 too. So if all of that has to be greater than 0, we could factorize this. So well, m can't be 0, g can't be 0, so we could probably just cancel these, although it's usually better to factorize, but sine 30 minus lambda has to be greater than 0. In other words, lambda has got to be less than sine 30, and sine 30 is a half, so lambda has to be less than a half.